Hey, and thanks for checking out my course, Neural Networks for Your Dog. So easy, your dog can learn them. This course is all about learning the fundamentals behind neural networks and deep learning. How do they work? Why do they work? Where do they shine? And where do they fall flat? The way we're going to figure these things out is by coding up a neural network from scratch in Python to recognize handwritten digits from the famous MNIST Dataset. So what separates this course from the dozens of other courses explaining neural networks? Well, it really comes down to fundamentals. By the end of this course, you're not going to have the skills to build a convolutional neural network in TensorFlow or deploy a recurrent neural network in PyTorch, but what you will have is a deep understanding of how neural networks work and an intuition about when they'll work, why they work, and in some cases, why they don't work. I mean, odds are most of you finding this course have some idea of what a neural network is, but even if you've watched a couple videos and read a couple articles about them, they probably still feel a little bit like a black box. If I asked you to code a neural network from scratch, could you do it? Probably not. So that's what this course is about, getting that deep, intimate knowledge about the fundamentals of neural networks. Once you have that, I promise that learning how to build production-level deep learning models with things like TensorFlow and PyTorch will be super easy, and you'll feel really confident in your work. I should warn you, we're going to use a lot of math in this course, but I've worked really hard to explain everything in great detail with examples and visual explanations, so don't let the math scare you. With that, I hope you'll stick around and take my course. As always, feel free to reach out to me if you have questions or comments. And if you appreciate my work, please consider liking, sharing, or subscribing so I can grow my channel and continue to put out quality content. Thanks. Hey, welcome to my course, Neural Networks for Your Dog. As I mentioned in the promo, this course is about understanding the fundamentals of neural networks, and I think the best litmus test for that is, can you code up a neural network from scratch? So we're not going to use TensorFlow, PyTorch, or any other neural network library in this course. We will be using Python, NumPy, and a little bit of Pandas. If you need to brush up on your NumPy or Pandas, check out my courses Python NumPy for your grandma and Python Pandas for your grandpa. As we go through the course, I'll be presenting various datasets, code snippets, challenge problems, and challenge solutions. I've taken the liberty of hosting these things on a public GitHub repo, ben519/innets for your dog. If you find my code useful, consider hitting that star button to help my course gain some traction. Also, I'm going to be using Google Colab, which is like a free Jupyter notebook for running Python directly inside your browser. I highly recommend learning it, although if you'd rather use your own IDE like PyCharm or Spider, that's fine too. My favorite thing about Google Colab is that training some of these neural networks can take a long time and a lot of compute resources. So running these things on Google Colab means they run on Google's machines, sparing my laptop from some wear and tear. Lastly, we're going to use a fair amount of math in this course. I'm going to try to explain everything in great detail, meaning I'm going to beat a few dead horses. But that's what this course is about, getting a really deep, intuitive understanding of neural networks. So without further ado, let's get into it. In this section, we're going to start our neural network journey with a classic motivational problem, identifying handwritten digits from the MNIST dataset. This is like the Hello World challenge of machine vision. The premise is we have 70,000 pictures of handwritten digits between 0 and 9. 50,000 of these represent the training data, where we know what digit the picture is supposed to represent. The other 20,000 represent the test data, where we have to predict what digit the picture represents. Each picture is just a 28 by 28 grid of grayscale pixel values, where each value is an integer between 0, which means black, and 255, which means white. To get a better understanding of this, let's download the data and start messing with it. Now, the MNIST dataset exists in a few different places, but I ended up hosting it on my own public GitHub repo so that you can read it directly into a Pandas data frame. I'll start by importing NumPy as NP, importing Pandas as PD, and I'll also suppress scientific notation and extend the default line width. Then I can set MNIST train equals pd.readcsv, passing in the public URL path of mnisttrain.csv from my GitHub repo. We'll ignore MNIST test until the very end when we have a model worthy of testing on some holdout data. So here's what the data looks like. And then if I call MNIST train.shape, you can see the training data has 50,000 rows and 785 columns, 784 of which are features. As I mentioned earlier, these 784 pixels make up a 28 by 28 grid. The first 28 features represent the first row of pixels, the second 28 features represent the second row of pixels, and so on. So if we pick out the first row of features, convert that to a NumPy array, and then reshape the 1D array into a 28 by 28 2D array using the default C-like index order, you can pretty much tell this is the number 5. All of these zeros are black pixels, and all of the non-zeros are basically white and gray pixels. Now, there's an easy way to plot this, so if we import matplotlib.pyplot as plt, and then do plt.mshow, passing in the 2D array we just created, set cmap equals gray, vmin equals 0, and vmax equals 255, you can pretty clearly see this is the number 5. We can confirm it by looking at the label for this training instance, like this. The challenge, of course, is how do you write a program to do this classification? So we'll take on that challenge in the next section. Our path to coding up a neural network starts with its most fundamental building block, the perceptron, a very simple linear binary classifier. To introduce it, we're going to work on a dataset even simpler than MNIST. We're going to work on a dataset I made up called MNIST. Like MNIST, I put the MNIST dataset on my public GitHub repo, so you can download it directly into a pandas data frame like this. The MNIST dataset represents 8 objects in my pocket with real-valued features x1 and x2, which you could imagine as the size and smoothness of each object, and a binary target y, indicating whether each object is a mint. When I reach into my pocket and touch an object, I want a model to predict whether or not it's a mint. If we plot the MNIST dataset on a coordinate plane colored by the target, it looks like this. There's an obvious separation between mints and non-mints. If we insert a line like this, then we have a model for classifying mints. Anything below the line we say is a mint, anything on or above the line we say is not a mint. Let's formalize that. So our model is a function f that makes a binary prediction about a point. In other words, the input to our model is a 2-element vector of coordinates, and the output is a 1 or a 0. So we can say f of x equals, and then we have 2 cases, 1 if x is below the line, and 0 if x is on or above the line, which we can simplify as otherwise. Note here that x is in bold to signify it's a vector of features, x1, x2. Now we have to formalize what it means to be below the line. Well, the line I drew here corresponds to the equation x2 equals negative 0.6 times x1 plus 0.9. For a point x1, x2 to be below the line means that x2 is less than negative 0.6 times x1 plus 0.9. So now we can complete our model as f of x equals the piecewise function 1 where x2 is less than negative 0.6 times x1 plus 0.9, and 0 otherwise. Now if I reach into my pocket and discover a new object with size 0.4 and smoothness 0.5, I can do some mental math and ultimately predict that it's a mint. This model, as you may have guessed, is a perceptron created by Frank Rosenblatt back in 1958. Let's see if we can generalize and formalize it a bit. Firstly, our data had two features, meaning we were operating in a two-dimensional space. So we described our separating line as x2 equals c1 times x1 plus a. In other words, a coefficient times x1 plus an offset. Now, what if we had three features? Well, then we could just do x3 equals c1 times x1 plus c2 times x2 plus a. And if we had n features, then we could use xn equals c1 times x1 plus c2 times x2 on up to cn minus 1 times xn minus 1 plus a. If we subtract xn from both sides, we can rewrite this as 0 equals c1 times x1 yada 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 plus an offset. And if we multiply both sides of that equation by a constant k, we get 0 equals k times c1 times x1 plus, well, you get it. Of course, a constant times a coefficient is just a different coefficient, and a constant times an offset is just a different offset. So we can rewrite this equation like this, where we usually call the w terms weights. This is the canonical form of a hyperplane in n-dimensional space. I should mention that this equation allows for multiple representations of the same hyperplane. For example, in 3 dimensions, the set of weights 1, 2, 3 with offset 0 represents the same exact hyperplane as the set of weights 2, 4, 6 with offset 0. But that's fine, we can worry about that minor detail later. Getting back to our perceptron, we can reformalize the model to support n-dimensional inputs like this. Except this is kind of wordy, so what most people do is they describe a vector of weights w and a corresponding vector of features x, and then you can rewrite this using a dot product between w and x. Alright, now let's get back to our 2D example with the MNIST dataset, and let's redescribe our model as f of x equals the piecewise function, 1 where w.x plus b is greater than 0, and 0 otherwise, where w equals the vector negative 0.6, negative 1, and b equals 0.9. So how did we come up with this model? Well, we basically looked at a graph of the data, and we saw where we could draw a line that separated green points from red points. The obvious next question is, how would you write a program to produce such a line? Well, there's a couple of important things we should point out. The first is that this data is linearly separable, meaning there exists a line that separates green points from red points. If our data looked like this, then it wouldn't be linearly separable because there's no line you can draw to perfectly separate green points from red points. There's a few lines that do a good job, but they're not perfect. This concept of data being linearly separable extends into 3 and higher dimensions as well. In 3 dimensions, if you have data like this, if you can separate green points from red points with a plane, then the data is said to be linearly separable. In the general case, if you have 2 sets of points x1 and x2 in Rn, if there exists a hyperplane in Rn such that every element in x1 lies on one side of the hyperplane, and every element in x2 lies on the other side, then the data is linearly separable. More formally, if there exists a vector of weights w and an offset b, such that w.x plus b is less than 0 for every x in x1, and w.x plus b is greater than 0 for every x in x2, then the data is linearly separable. For example, if we're in R4, then x1 might represent this set of points, and x2 might represent this set of points. Looking at the equation for a hyperplane in R4, the question is, can you come up with a set of weights w and an offset b such that plug in every point from x1 and you'll get back a value less than 0, and plug in every point from x2 and you'll get back a value greater than 0. If there exists a set of weights and an offset that do that, then x1 and x2 are linearly separable, otherwise they're not. This brings up another fascinating question. Given a random dataset with 2 classes, how do you figure out if it's linearly separable? We'll circle back to answer that question, but in the meantime, let's assume that every dataset we're going to work with is linearly separable. The second thing to note about the MNIST dataset is that there's a lot of different lines we could have picked to separate the data. We arbitrarily chose this one, but we could have picked this one, or this one, or this one. Of the infinitely many lines that separate the data, one line of particular interest is this one because it goes right down the middle of the gap between red and green dots. This is what's known as a maximum margin classifier because it has the biggest possible margin on both sides. Finding this guy is the objective for support vector machines, aka SVMs. Unlike support vector machines, perceptrons aren't so needy. The goal of a perceptron is just to find any line that separates the classes. Let's get back to our big question. Given a set of data with a binary label, assuming the data is linearly separable, how do we find a hyperplane that separates the class labels? Take a moment to really think about this. How would you do it? It's not exactly trivial. A good way to approach problems like this is to start with a really dumb but simple solution. This will help you wrap your head around the problem and develop an interface for inputs and outputs. So what's a really dumb but simple way we could find a separating hyperplane for some set of data? Well, let's use my favorite algorithm, guess and check. Just randomly guess some weights and an offset and check if they separate the data. If they do, we're golden, and if they don't, just keep guessing. My challenge to you is to write a program that does this. To help you get started, I created a Python file called 2.2 challenge, which contains some starter code and references to some known separable datasets. I also made a function called plot dataset, which lets you plot a 1D, 2D, or 3D dataset with a hyperplane. So pause the video and see if you can implement a guess and check program for finding a separating hyperplane. Before I explain my code for my guess and check algorithm, let me explain the logic. Rather than guess truly random hyperplanes, I wanted to guess hyperplanes that at least cut through the data. To do this, I imagined putting a bounding box around the data and then selecting a random point within the bounding box. From there, I guessed random values to determine the slope of the hyperplane by guessing random weights, and then I solved for the offset b to force the hyperplane to go through p. So here's my code. I start by creating a NumPy random generator. If you're not familiar with this, check out my lecture on random number generation with NumPy. Then I set up a for loop to do max guesses iterations. Next, I determine the bounding box of the data by getting the min and max value of every feature dimension. Then I randomly guess weights between -1,000 and +1,000, which is somewhat arbitrary, but that's fine for now. Next, I pick a random point, p, in the bounding box, and calculate b such that my hyperplane goes through p. Keep in mind that if the hyperplane goes through p, it means that w.p plus b equals 0, so b equals -w.p. Lastly, I check if the hyperplane separates the data. So if the hyperplane separates the data, it means where y equals 1, x.w plus b should be positive, and where y equals 0, x.w plus b should be negative. We can imagine the hyperplane making a prediction about each point, and if all the hyperplane's predictions match the true labels, we know it's a separating hyperplane. Note that np.sign returns 1 if the input is positive, 0 if the input is 0, and -1 if the input is negative. And since our data is labeled with 1s and 0s, not 1s and -1s, we have to transform the predictions into 1s and 0s as well. Also note that if a point lies directly on the hyperplane, meaning x.w plus b equals 0, then we consider it misclassified. Now let's take what we've built and generalize it into a reusable model. Here I've taken our guess and check function and refactored it into a Perceptron class with some extra pizzazz. Namely, my Perceptron class has 3 methods. An init method for directly building a perceptron if you know W, B, and Y classes ahead of time, a fit method for fitting a perceptron to some data using the guess and check learning algorithm, and a predict method for using a fitted perceptron to make predictions on new data. Note that fit here allows y to be a NumPy array with any binary class labels. So instead of 1s and 0s, y could have 1s and -1s, or trues and falses, or a's and b's, or whatever, as long as it has exactly two distinct classes. Also, in the fit method, we don't allow a point to lie exactly on the separating hyperplane. But in the predict method, if it happens that a point falls on our separating hyperplane, we arbitrarily predict class 0 for the sample. Let's see this puppy in action. We'll start by reading some data into a data frame called df. Then we'll initialize a new perceptron object. Then we'll fit the perceptron to the first 80 rows of the data. And then we can use the fitted perceptron to predict on the last 20 rows of the data. Take some time to study this code, because we're going to be refactoring it in the next section. Now that we've got our feet wet implementing a dumb but simple algorithm for finding a separating hyperplane, I'll do my best to explain the canonical algorithm. The algorithm itself is pretty simple, but not obvious. And even when you see it, it's not obvious it should work. The first thing we're going to do is tweak our definition of a perceptron. Since it's somewhat inconvenient to maintain a vector of weights and an offset, let's see if we can, in a sense, get rid of the offset. Recognize that w.x plus b is the same thing as the vector w with b appended to the end of it, dotted with the vector x with 1 appended to the end of it. So if we tack on a column of 1s at the end of our feature matrix x, and we tack on b to our weight vector w, we can redefine our perceptron as f of x equals the piecewise function, where we predict 1 if w.x is greater than 0, and 0 otherwise. Now our separating hyperplane is defined entirely in terms of our weight vector w. What comes with this is a really interesting geometric interpretation. Let's picture a really simple dataset with two samples in one dimension, a red dot and a green dot on the x1 axis like this. A separating hyperplane in 1D is just a point that exists somewhere in this gap. Now, when we modify x, tacking on a column of 1s, we're increasing the dimensionality of x. So points on this line suddenly become points in this 2D plane. Of course, they all have x2 equals 1, so they still lie on a 1D line, but now they exist in 2D. So what are all the hyperplanes that could separate this data? Well, there's this guy, and this guy, and this guy, and so on. So you might actually think we just made the problem harder, because now there's all these additional lines in 2D that we have to consider in our search. But wait, we got rid of our offset b. What that means is that we only have to consider lines that go through the origin. So we don't have to worry about this guy, or this guy, or this guy. I'll convince you that's true in a second, but let's go back to one dimension. Pick any point on this line. I'll pick a few of them actually. Now, imagine this data rising up into 2 dimensions. It's visually clear that for any point we could have picked on this line, we can find an equivalent line in 2D that goes through the origin. So, increasing the dimensionality of the data like this isn't going to be more restrictive than just searching for a separating point in 1D. Okay, so how do I convince you that we're searching for a separating line that necessarily goes through the origin? You may recall the dot product has 2 very different but equivalent formulas. The first is that given a vector A and a vector B, A dot B is the sum of the product of their corresponding elements. This is the definition we've been using. The second is that A dot B equals the length of A times the length of B times cosine of the angle between them. The equivalence of these 2 definitions isn't totally obvious, but there's some good proofs of this online, so I'll leave it to you to look those up on your own time. Looking at this definition, how could it be possible that a dot b equals 0? Well, either one or both of the vectors has length 0, or cosine of the angle between them is 0, which means the angle between them must be 90 or 270 degrees. In other words, they must be perpendicular. So, thinking about w dot x equals 0, if you imagine the weight vector pointing out into space somewhere, then the set of vectors x such that w dot x equals 0 is the set of all vectors perpendicular to w. For example, in 2D, if our weight vector looks like this, then the corresponding hyperplane it defines looks like this. In 3D, if our weight vector looks like this, then the hyperplane it defines looks like this. Alright, so let's say we have a data set like this, and then we randomly pick a weight vector like this, which means our hyperplane looks like this. By the way, which side of the hyperplane is the positive side? Meaning, for which side are we predicting positive 1? Well, remember w dot x equals the length of w times the length of x times cosine of the angle between them. So draw a vector on this side of the hyperplane. The angle between w and v is less than 90 degrees, so cosine of that angle is positive, which means the dot product is also positive. So when you see this picture, it's easy to remember. The vector w points in the direction of positive predictions. Okay, so we have this weight vector, which defines this hyperplane, which predicts positive for both of these samples, which means this red dot is misclassified. So how do we improve the decision boundary? Well, we can't shift it because it has to go through the origin. So we want to rotate it a little bit counterclockwise. And we want that update to be dictated by this misclassified point. So what we can do is, if you imagine the vector pointing to this red dot, if we subtract that vector from w, the decision line rotates in the direction we want it to go. Alright, clearly we overshot. Nonetheless, let's just keep going with this idea. So in this case, we predict 0 for both samples, which means this positive sample is misclassified. So this time, let's add this vector to our weight vector. And voila, we have a separating line for the data. This process is essentially the learning algorithm for a perceptron. More formally, the algorithm goes like this. Initialize w equal to the 0 vector, that is a vector of all zeros. While at least one x is misclassified by w, pick an arbitrary misclassified x and update w to be w minus x if x is a negative sample, or w plus x if x is a positive sample. Keep in mind that if x lies on the hyperplane defined by w, we always call it misclassified. This is a fascinating algorithm because, at least to me, it's not obvious that the algorithm necessarily converges onto a separating hyperplane, assuming one exists. But it does, and it does it in a finite number of steps. Looking back at this example, it seems totally plausible that there may be a separable dataset where the hyperplane just bounces around forever as we make updates. But to the contrary, if the data is separable, this thing converges. So for your next challenge, see if you can implement the code for this algorithm by refactoring the code for the Perceptron class from the last section. Here's the implementation I came up with. Firstly, note that I adjusted the init and predict methods to assume the offset b is embedded in the weight vector w. Inside the fit method, I define x1 as x with a column of 1s inserted at the end. I use a while loop with two indexers, I and j. I iterates over the rows in x, searching for a misclassified sample, and j keeps track of the total number of iterations. y hat I is the label assigned to xi by the current hyperplane. If y hat I doesn't equal the true label for the ith sample, then I update w as either w plus xi or w minus xi, depending on whether the true label is positive. And as soon as I make a weight update, I reset I back to 0 so the program goes back to the beginning of x, searching for a misclassified point using the updated weight vector. Once the program scans every element of x without finding a misclassified point, it updates the class attributes y classes and w. Alternatively, if max iters is reached, the program throws an error. Let's test it out on our known separable 2D dataset, just like we did in the last section. Empirically, this thing seems to work, but it almost feels like we're just using a heuristic, and maybe there's a scenario where this algorithm fails to converge on a hyperplane that we know exists. By the way, if there's no hyperplane that separates the data, the algorithm just loops forever, or at least the canonical version does. After all, the algorithm's stopping condition is literally that the current hyperplane separates the data. So, assuming the data is linearly separable, how do we know for sure that this thing converges? It turns out there's a fairly elegant, but not exactly simple convergence proof. I debated explaining this proof in this lecture, but honestly, it's kind of hard to explain in a way that's quick and interesting, so I'm going to take the cheap way out and refer you to this really nice write-up by, okay, here we go, Shivaram Kalyankrishnan. Alright, now let's see if we can apply our Perceptron model to the MNIST dataset. Since the MNIST dataset has 10 target classes, and perceptrons are mere binary classifiers, we have to conjure up a simple binary classification problem. So, instead of predicting which digit each image represents, let's just see if we can predict whether each image is a 0 or not a 0. Hopefully this thing converges. Crap, it didn't converge. What does that tell us? Unfortunately, not much. I mean, it's an indicator that the data is not linearly separable, but it's possible that we just didn't run enough iterations. This resurfaces a nagging question. Given a set of data with 2 target classes, how do you know if it's linearly separable? Is there a simple test that can tell us, yes, the data is linearly separable, or no, it's not? It turns out, yes, there is a conclusive test to determine whether a dataset is linearly separable. The answer is linear programming. Briefly, for the uninitiated, a linear program is an optimization problem that can be expressed as maximize C transpose X, subject to AX is less than or equal to B, and X is greater than or equal to 0, where C is a fixed vector, A is a fixed matrix, B is a fixed vector, and X is the vector that the program tries to optimize. Lots of optimization problems can be restructured as a linear program. Restructure a problem like this, and then you can plug it into a linear program solver, LP solver for short. Magic happens, and you get back a solution. If you've ever heard of the simplex algorithm, that's a famous solution to a linear program, but it's been improved upon many times since its creation in 1947. Once again, there's some tedious math to explain how this works, so I'll spare you the details, but this article by Raphael Vogler helped me understand them. I even ended up rolling my own isLinearlySeparable function that uses SciPy's linprog method to check if a dataset is linearly separable. And as it turns out, when you look at zeros versus non-zeros in the training portion of the MNIST dataset, they're not linearly separable. But if you take a random sample of 5,000 rows from the training dataset, zeros versus non-zeros usually is linearly separable, which means even though zeros versus non-zeros aren't completely linearly separable, there's a hyperplane somewhere that does a pretty good job of mostly separating zeros and non-zeros. If we could find that hyperplane, we'd probably end up with a pretty good classifier. I should also mention that if the linear program solver converges, it necessarily has found a separating hyperplane. What's interesting about this is LP solvers like the simplex method existed before Frank Rosenblatt created his perceptron learning algorithm. So, unless I'm mistaken, Frank could have just used an LP solver. We ended the last section a little bit deflated because we figured out that the MNIST training data of zeros versus non-zeros is in fact not linearly separable. But we also discovered that it's almost linearly separable. So if we could figure out a way to tweak our perceptron learning algorithm to learn a hyperplane that mostly separates the target classes, it could still be a strong predictive model. A simple but effective way to do this is the pocket algorithm, where as you make weight updates, you keep track of the best performing weight vector, placing it in your pocket, and unveiling it at the end of some predetermined number of iterations. This idea was originally described by Stephen Gallant in 1990, but I suggest we make a couple tweaks to the algorithm he proposed. The algorithm I challenge you to implement goes like this. Initialize wpocket equal to the zero vector, wcurrent equal to the zero vector, wpocket accuracy equal to 0, and wcurrent accuracy equal to 0. Then set accuracy current equal to accuracy of wcurrent applied to the full training data. Next, if accuracy current equals 1, meaning the current weight vector does a perfect job of separating the target classes in the training data, we return wcurrent. Otherwise, if accuracy current is greater than accuracy pocket, we set wpocket equal to wcurrent and accuracy pocket equal to accuracy current, meaning if the current weight vector does a better job than the weight vector in our pocket, we update what's in our pocket. Then we identify a random training sample such that wcurrent misclassifies it, and we use it to update wcurrent with the canonical update procedure. Next, we repeat steps 2 through 4 until some stopping condition is met. For example, we might run 1,000 iterations. And then lastly, we return wpocket, which should be the best weight vector we found. So pause the video and see if you can refactor the perceptron class from the last section to use the pocket algorithm in case the training data is not linearly separable. Here's my implementation. I start by initializing a bunch of stuff, like a random number generator, x1, wcurrent, wpocket, accuracy current, and accuracy pocket. Then I set up a for loop to run max updates iterations. Next, I use wcurrent to make predictions on all the samples in X, and then I measure its accuracy rate. Then I do a couple checks. So if accuracy current is 1, meaning the hyperplane defined by wcurrent perfectly separates the target classes, I set wpocket equal to wcurrent, and then I break out of the for loop. Alternatively, if accuracy current is better than accuracy pocket, I set wpocket equal to wcurrent and accuracy pocket equal to accuracy current. Assuming we're still in the for loop because we haven't found a hyperplane that perfectly separates the data, the next thing I do is I pick a random training sample such that wcurrent misclassifies it, and I use it to update wcurrent with the same update procedure as the canonical perceptron learning algorithm. Once we're out of the for loop, I simply update the class attributes self.yClasses equal to yClasses and self.w equal to wpocket, which is the best performing weight vector we found. Let's test our model on the unseparable 2D dataset. You can see how it did a pretty reasonable job of finding a separating line. Now let's test it on MNIST zeros versus non-zeros. I'll set verbose equals true here so we can see how the model improves quickly at first and slowly towards the end. The takeaway here is that even though we can't perfectly separate zeros and non-zeros with a hyperplane, we can get pretty darn close. Now, we still don't have a multi-class classifier. So given an image, I can't tell you if it's a 1 or a 5 or a 9. All I can tell you is if it's a 0 or not a 0. So the obvious next question is, how do we extend our binary classifier into a multi-class classifier? In the last section, we ended the lecture by asking ourselves, how can we convert our perceptron, a binary classifier, into a multi-class classifier? Two popular techniques for doing this are one versus rest and one versus one. The idea behind one versus rest is, suppose you have 4 target classes, A, B, C, and D. Then you train 4 binary classifiers, A versus not A, B versus not B, C versus not C, and D versus not D. Given a new sample X, you have each classifier make a prediction about X. So ideally, each classifier outputs some sort of score, like a probability, and then you just pick the one with the highest score. With one versus one, you'd train 6 binary classifiers, one for each pair of classes. Given a new sample X, have each of them make a prediction, and then let them vote on the most likely target class. Of course, it's possible to have ties, so it requires a tie-breaking mechanism, which usually means it requires some sort of score function, just like one versus rest. So, how could we implement a one versus rest system for our perceptron? Take a look at this dataset and separating line. Hopefully, it's intuitive that the distance between a point and the line coincides with how confident we can be about the model's prediction. So, given some point x, the score we should give it is its distance to the hyperplane. And ideally, that means we should use the hyperplane with maximum margin between the two classes, i.e. the one found by support vector machine, but we'll settle for whatever hyperplane the perceptron gives us. So, see if you can implement a one versus rest system to turn our perceptron into a multi-class classifier. Here's the code I came up with. So, before I was using a lowercase w to store a 1D array of weights. Here I use a capital W to store a 2D array of weights, where the kth column of the array represents the weights for the model that predicts class K versus not class K. In other words, each column of the array represents a different perceptron. With that modification in place, my fit method is pretty self-explanatory. It's basically the same as it was before. I just have an extra loop that iterates over each target class, finding the best weight vector for the model, class K versus not class K. Now, there is a significant change to the predict method. For each test sample X, we need each perceptron to tell us the distance between X and the hyperplane. So, given some weight vector W and a new sample X star, how do we determine the distance between X star and the hyperplane defined by W? Well, the shortest distance between the hyperplane and X star is going to be given by a vector V, perpendicular to the hyperplane that touches the head of X star. So our goal is to find the norm of V. And let's define XP as X star minus V. Well, we know W.XP equals 0, which means W.X star minus V also equals 0. At this point, recognize that since V and W are both perpendicular to the hyperplane, V is just a scaled version of W. In other words, there's some constant alpha such that V equals alpha times W. So we can restate the previous equation as W dot X star minus alpha times W equals 0, which we can rewrite as W dot X star minus alpha times W dot W equals 0, which we can rewrite as W dot X star equals alpha times W dot W. And the only thing we don't know in this equation is alpha, so let's solve for alpha. We get alpha equals W dot X star divided by W dot W, which is the same thing as w.x star divided by the norm of w squared. So we want to find the norm of v. Well, the norm of v equals the absolute value of alpha times the norm of w. Plugging in our definition for alpha, we get the norm of v equals the absolute value of w.x star divided by the norm of w. Getting back to the predict method, once we set up x1, we calculate the distance of each point to the hyperplane for each class, except we don't just calculate the distance, we calculate signed distance. And this is important. If we only knew the distance between a point in the hyperplane, it wouldn't tell us if the model is voting for or against a certain class label. So we need signed distances to keep track of which models are leaning for or against each class label. So sign dists is a in-row by k-column array of positive and negative distances. And then for each row in sign dists, we determine the column with the largest value because that's going to be the most confident prediction for a particular class label. Lastly, we look up the class corresponding to that column index. Let's give this puppy a whirl in the MNIST dataset. With max updates set to just 100, we're able to achieve 85% accuracy. When I let this thing train with max updates set to 1000, it actually gets 89% accuracy. Not bad, considering we're using mere hyperplanes. By the way, if this is the first image classification model you've coded from scratch, go ahead and pat yourself on the back. Getting to this point is a pretty cool achievement. Big question. Why do perceptrons work? Well, we've alluded to the fact that these images are points in a 784-dimensional space. We can't visualize it, but theoretically they sort of live in clusters, where each point that represents a 0 sort of lives in the same neighborhood, and each point that represents a 1 sort of lives in the same neighborhood, and so on. And so it makes sense you could use hyperplanes to partition this 784-dimensional space in a way that separates these clusters from one another. But there's another, probably more intuitive way to think about what's happening. This concept was first introduced to me by Michael Nielsen, the author of Neural Networks and Deep Learning, which is a fantastic free online book. We'll start by analyzing the submodel we trained in the last section that predicts 0 versus not 0. The weights for that model are stored in the first column of p.w, so we'll extract those. And then we'll normalize them so they're a little more comprehensible. Here, we're normalizing the weight vector to have length 1. So what does our model look like? Well, it looks like this. Let's move the offset to the right side. So now we have this. Now let's take a look at a typical 0. Keep in mind that pixel values go from 0 meaning black to 255 meaning white. We can think of this model almost like a game. Negative b here is our threshold, and in our 0 versus not 0 model, negative b equals 0.0008. We start at 0, and then we move up or down the amount of each of these products. If we end up above the threshold, we predict 0, and if we end up below the threshold, we predict not 0. Now let's hone in on this top left pixel, pixel 0. The weight associated with this pixel is 0, so it actually doesn't matter whether this pixel is white or black. It has 0 effect on our model. It's sort of like our model is saying that this pixel is completely irrelevant in classifying zeros versus non-zeros. That turns out to be the case for a lot of these terms, so let's get to a more interesting pixel, pixel 353. The weight for this guy is negative 0.17. It's the most negative weight in the entire weight vector. So the brighter this pixel is, meaning the higher its value, the more evidence we have against this image being a 0. Looking at this example of a 0, you can see that this pixel is black, meaning the pixel's value is 0. So this term doesn't contribute anything to the overall score. If you look at where this pixel lies on some other training images, you can see that amongst zeros, it's almost always black, but amongst other digits, it's commonly gray or white. So the negative weight for this feature makes a lot of sense. Now let's check out pixel 540. The associated weight here is 0.09, the highest positive weight in the model. So anytime an image has a bright white value here, it's strong evidence for a 0. Looking at some examples, you can see it lies here, a common place for zeros, but not so common for other digits. Closing out this particular example, you can see we end up with a final score of 240.05, far above the 0.0008 threshold, so our model predicts that this image is a 0. Looking at the bigger picture here, you can see how the sign of each weight determines if brightness in a pixel is evidence for or against the thing you're classifying, and the magnitude of each weight determines how important each pixel is. And the offset, B, determines how much collective evidence is required to make a positive classification. In fact, if we plot the entire weight vector of our 0 versus not 0 model onto a 28 by 28 grid, you can see how the weights themselves practically draw the number 0. So when we think about perceptrons in this way, it's actually a really intuitive and logical model. Even if we didn't have a learning algorithm, we could probably conjure up sensible weights by hand. I mean, it'd be painful, but just by looking at a handful of images, you could determine which pixels, when lit up, provide strong evidence for 0, and which pixels provide strong evidence against 0. The learning algorithm just gives us an automated way of learning the weights, but the model itself and why it even has a chance at classifying zeros versus non-zeros, that's what's really important here. With that said, the perceptron still has a big pitfall. Before I explicitly state what that is, let's think about a simpler problem. Suppose you want to build a model that predicts whether it's a good day to play tennis. This model has 3 inputs, all of which are binary features. Is it sunny? Is your friend Jeff available to play? And is your friend Kit available to play? Challenge: handcraft a perceptron for these inputs that's equivalent to the following program. If it's sunny and Jeff is available or Kit is available, predict 1. Otherwise, predict 0. Here's the weights and bias I came up with. It's easier to think of the bias as a threshold, so I'm going to move it to the right-hand side. So in order to predict, yes, it's a good day to play tennis, you can see how it has to be sunny. If it's not sunny, there's no way we can get above the threshold. And if it is sunny, we get to 2, which means all it takes is one of Jeff or Kit to be available for us to get above 2. So we just built a perceptron that's equivalent to a simple logical program. Now, there's a picture we can draw to represent this model. It looks like this. It's no coincidence that this picture kind of resembles a neuron, like the ones in your brain. So, if you don't know much about neurons, neurons are the building block for the electrical system in your brain. A human has about 86 billion of these guys, and on average, each neuron is connected to about 7,000 other neurons. A single neuron has 3 main components: dendrites, which receive input signals from other neurons, a cell body called the soma, and an axon, which transmits a signal to other neurons. Basically, the way neurons work is they receive signals from other neurons, and then they typically have an all or nothing response where they either transmit a signal down their axon or they don't. Note that there are many different types of neurons, and some of them actually have a graded response, but the ones we're interested in are the neurons that have the all or nothing response. So, in regards to these, we usually describe the neurons as firing or not firing. Notice how similar this is to our model of a perceptron. Alright, here's another challenge that builds off our previous challenge. You've noticed that when Jeff and Kit are both available, they tend to play each other, leaving you partnerless. So, you need to devise a new perceptron that predicts 1 if it's sunny, and Jeff or Kit is available but not both, and 0 otherwise. Hopefully you didn't spend too much time on this because it's not possible. This setup suffers from what's known as the XOR problem, famously described by Marvin Minsky in a 1969 book called Perceptrons. In fact, you could rewrite the pseudocode for our problem using an XOR operator like this. It turns out, perceptrons can't mimic the very simple XOR gate. Visually, this is analogous to trying to separate this data with a line. Clearly, the perceptron has a big issue, but with a few clever tricks, we can overcome it. Inspired by our understanding of the brain and how the output of one neuron becomes the input to another neuron, what if we tried connecting multiple perceptrons together? Does that give us some sort of advantage and perhaps the ability to solve the XOR problem? Spoiler alert, it does. So see if you can handcraft a network of perceptrons to solve our previously unsolvable tennis program. Here's the perceptron network I devised that solves the challenge problem. In case it's not clear from the picture, the signal going into each node is the dot product of the edge weights and the nodes they connect from, and the signal coming out of each node is a 1 or a 0, depending on whether the input signal was positive, with the exception of the first layer of input nodes. Let's see how my perceptron network works. Firstly, recognize that this X*1 node only fires if it's sunny. This X*2 node only fires if Jeff or Kit are available. And this X*3 node only fires if Jeff and Kit are available. Lastly, if you focus on the output perceptron, it should be clear that it only outputs 1 if it's sunny and Jeff or Kit is available but not both of them. If you need to, pause the video and run through some cases to convince yourself this is true. Also note that I could have inserted lines like this to indicate weights with value 0, but I excluded them to keep the picture simple. Now take a step back and think about what we've created here. We have a model that can generate complicated nonlinear decision boundaries in a really intuitive structure that mimics logic. This model is called a multi-layer perceptron, aka a neural network. Clearly, this model could be a really powerful predictor. The elephant in the room is it's not obvious how to learn the best weights from a training dataset. The learning algorithm we had for a perceptron immediately becomes unusable once we start connecting perceptrons together. So our focus at this point is, given a training dataset which no longer needs to be linearly separable, how do we learn the weights and the structure of a neural network that accurately classifies the data? To motivate the learning algorithm for a neural network, I've cooked up an image classification problem that's a good bit simpler than classifying handwritten digits. I created a dataset of 5,000 simple images where each image falls into one of 3 categories: checkerboard, bright line, or triangle. Just like MNIST, these images are made up of grayscale pixel values, ranging from 0 meaning black to 255 meaning white. I also randomly partitioned the data into a training set with 4,000 images and a test set with 1,000 images. This will give us a nice, super simple motivational problem for fleshing out the details of implementing a neural network. And just like the MNIST dataset, I put the simple images data on my public GitHub repo so you can read the data directly into a pandas data frame. For example, you can load simple images train.csv into a data frame like this. And then if you wanted to plot the first image, you could do that by dropping the label column, casting the data frame to a NumPy array, selecting the first row, reshaping it into a 2x2 array, and then passing that 2D array into pyplot's imshow method like this. So our goal from this point onward is to design and implement a neural network that can learn to distinguish between these three classes of simple images. Once we have a network that can do that effectively, we should be able to just plug in the MNIST dataset and have it learn to recognize handwritten digits without making any modifications to the internals of our model. Our job today is to design and implement a neural network to classify simple images in our dataset of checkerboards, bright lines, and triangles. So where do we even begin? Well, when we finished talking about perceptrons in the first section of the course, we handcrafted a neural network to predict whether it's a good day to play tennis. Using a similar thought process, if we had to devise a neural network to classify simple images, a network design we might come up with could be something like this. A quick note about terminology here. We have three layers of nodes. The layer to the far left is the input layer, the layer to the far right is the output layer, and the layer in the middle is what's called a hidden layer. Also recognize the perceptrons embedded in this model. Since this thing has two layers of perceptrons, some people would call this model a multi-layer perceptron. So how did I dream up this network? Well, our data has 4 features, so I know for certain it should have 5 input nodes, 4 feature nodes plus a bias node fixed equal to 1. I really don't know how many nodes the hidden layer should have, but I arbitrarily guessed 5, one of which is another bias term. I also don't know how many hidden layers I should chain together, but to keep things simple, I decided to start with just one hidden layer. And for the output layer, I know it has to have one node because I'm designing this model to be a binary classifier, just like a typical perceptron. Later on, we'll see how we can extend this model to have multiple output nodes. The big question here is, what should the weights be? You can see I conveniently excluded them. We'll get to that in a second. By the way, this is how neural networks are typically depicted, but I like to add a set of nodes whose job is to sum the weighted inputs into a scalar, and then pass that scalar onto these subsequent nodes, which look at those incoming signals and decide whether to fire or not fire. Meaning, they look at the incoming signal, and if it's greater than 0, they pass on the value 1, otherwise they pass on the value 0. Let's run through a simple example just to make sure we're on the same page as to how this works. First, let's assume that somehow we've come up with the following weights for our network. Then the first simple image in the training data looks like this. So for training sample 0, the input pixels would get set to 200, 52, 58, and 199, plus the bias term which is fixed equal to 1. Then if we focus on the first perceptron, we'd calculate a signal which we'll call z equal to the weighted sum of the inputs, which ends up being 12.37. So then we could do the same thing to calculate the signal going into every hidden node. And then, per the usual perceptron rules, the first 2 hidden nodes would fire because their signals are greater than 0, and the last 2 hidden nodes wouldn't fire because their signals are not greater than 0. So the outputs of the hidden layer, 1, 1, 0, and 0, plus the hidden layer bias term, become the inputs to the next layer, the output layer. So then we just do the same exact thing and ultimately calculate our prediction, y hat, for this sample as 1. Notice that once again, we have a multi-class classification problem because we have 3 target classes, and a binary predictor, because for a given input, our model spits out a 1 or a 0. So we have to simplify our problem. For the time being, let's just try predicting whether each image is a checkerboard or not a checkerboard. Challenge: implement a neural network class with this structure. Give it a fit method and a predict method, just like we did with our Perceptron class. For the fit method, randomly guess 10,000 different sets of weights and keep the weights that produce the best predictions. Here's the code I came up with. But before I explain it, I think it'll help to add more context to the network diagram we're working off of. First of all, what does our input look like? Well, we've got two matrices, i.e. NumPy arrays. X is a tall matrix with n rows and 4 columns, and Y is another tall matrix with n rows and 1 column. However, in my code, X is a 2D array, but Y is a 1D array, so keep that in mind. Next, X has 4 columns, but the input layer of our neural network has 5 nodes. So just like we did with our Perceptron model, we immediately convert the input X into a matrix which is just a copy of X with a column of 1s appended to the end. Next, let's deal with this first set of edges, i.e. the weights. Each weight has a natural subscript pair, from node to node, or to node from node. People make different choices here, but I'll go with from node to node. So then the weights can be organized into a matrix, i.e. a 2D array, like this, where the number of rows corresponds to the number of from nodes, and the number of columns corresponds to the number of to nodes. Another way to think about the weight matrix is that each column corresponds to a perceptron in the first layer of perceptrons. The second weight matrix follows the same pattern, but then we have this issue of distinguishing the first weight matrix from the second weight matrix. So we'll introduce superscripts like this. Next, we'll deal with these bold dots that represent the weighted sums of the prior layer of nodes. We'll label these guys Z, also with a superscript to distinguish the first layer of Z's from the second layer of Z's, and subscripts I and J, where I represents the ith input sample, and J represents the jth signal in the respective layer. So the Z matrices end up looking like this. Next, we have the hidden layer nodes. You may have noticed a striking similarity between the hidden layer and the input layer. They do the same exact thing, just at different stages in the network. In other words, the hidden layer nodes can be interpreted as inputs to the rest of the network. So, just as we labeled the input layer like this, we can label the hidden layer like this. And then of course, we'll give these guys superscripts to distinguish between them. At this point, we've notated everything in our network, but we should clarify some definitions. Let's focus on Z1. Picking out the first element of Z1, we see that it's equal to the first row of X1 dotted with the first column of W1. Similarly, Z112 equals the first row of X1 dotted with the second column of W1. Following this pattern, you can see that the matrix Z1 equals the matrix product of X1 times W1. Similarly, the matrix Z2 equals the matrix product X2 times W2. Now, what about X2? Ignoring the last column for a second, X2 equals 1 where Z1 is positive and 0 otherwise. A functional way to write this is h of Z1, where h is the Heaviside step function, defined as h of x equals 1, where x is greater than 0, and 0 otherwise. So we get X2 equals the matrix h of Z1 with a column of 1s appended to the end. And then y hat is defined nearly the same way. Lastly, I should mention that the process of making these calculations all the way from input to output is what's called the forward pass. Let's see how I implemented this in code. The first thing I do is I define a helper function called Heaviside, which inputs a 1D array of real numbers, x, and outputs a corresponding 1D array of 1s and 0s using the Heaviside step function. Then I define a neural net class with 3 methods. Init, which allows me to initialize a neural network, optionally passing in W1, W2, and Y classes ahead of time if I already know what they should be. Fit, which does the heavy lifting of learning the best weights given some training data. It's also in this method where I determine the structure of the network. I'll explain that in a second. And then predict, for making predictions on new data, assuming we've already trained the network. So the fit method takes 5 arguments. X, a 2-dimensional NumPy array of real-valued features. Y, a 1-dimensional NumPy array of 2 distinct target classes, like 1s and 0s, trues and falses, or A's and B's. Hidden nodes, a scalar that says how many hidden nodes to use in the hidden layer, excluding the biased node. Guesses, which is by default set to 10,000, which means how many guesses to make. And seed, by default set to none, an optional random seed you can pass in to get reproducible results. The first part of the fit method is just recycled code from the Perceptron class, where I validate the input and create Y01, which converts the inputted Y array to an array of 0s and 1s. Then I initialize a random number generator. I set x1 equal to x with a column of 1s appended to the end of it, and then I set up variables to track the best weights and accuracy. Next, I enter a for loop that runs guesses iterations. Inside the for loop, I start by randomly assigning weights to W1 and W2. The only sneaky thing about my code here is since I use uniform random weights between -1 and +1, and I know my inputs vary between 0 and 255, I want to pick random biases in the first layer that could overcome the inputs, meaning I wanted the range of my bias term to be the same as the range of the sum product of the input features and weights. Otherwise, the bias is rarely going to have any effect on the model. After I set up the weight matrices, I do some basic matrix math to determine Z1, X2, and Z2, and ultimately Y hat. Again, this is what's referred to as the forward pass. It's pretty critical that you understand what's happening here, so if you don't, I suggest you pause the video and step through the code with some toy data until it makes sense. And then from here, I just measure the accuracy of the current weights, and if they're the best ones seen thus far, I store them in the variables best W1 and best W2. Once the loop completes, I just update the class attributes Y classes, W1 and W2. And then the predict method is pretty self-explanatory. It's just a forward pass on some new X data using the weight matrices stored as class attributes W1 and W2. Let's see this thing in action. I'll start by reading in the simple images training and test data. Then I'll initialize a new neural network object and fit it to the training data, setting y equal to train.label == checkerboard. And now I can evaluate it by making predictions on the test data. You can see it's about 70% accurate in classifying checkerboards. Now that we've built a neural network that randomly guesses weights, how do we devise an algorithm that smartly learns better and better weights? Suppose we initialize some random weights, and then we very slightly increase W111. Given that small increase in W111, how will the accuracy of our predictions change? It'd be useful if we could estimate the change in accuracy with respect to a small change in W111. If we knew this and we knew it for every weight, we could implement a procedure where we iteratively increase or decrease the weights a small amount in the direction that improves the overall accuracy. This process is known as gradient ascent, which is just the inverse of gradient descent, a classic and very popular optimization algorithm. Here's a quick primer on gradient descent. Suppose you have a function like 2x² - x + 1, and you want to find where the function achieves its global minimum. The way you learned to do this in calculus was to calculate the derivative of the function, 4x minus 1, set that equal to 0, solve for the critical points, and then test those to see if they're mins, maxes, or saddle points. But suppose instead the function was 1/6 x to the 6th minus 1/2 x squared minus x, the derivative of which is x to the 5th minus x minus 1. Set that equal to 0, and you're left with the nasty job of finding the roots of a 5-degree polynomial. Gradient descent helps with functions like this, where finding the critical points directly with calculus is hard. It works as follows. Suppose you want to find an x that minimizes some function f of x, which some people write as argmin sub x f of x. Start by picking a random x star. Next, calculate the derivative of f with respect to x, evaluated at x star. Then, step in the direction of the negative derivative. Typically, the step size here is called alpha, so you end up with x star is updated as x star minus alpha times the derivative of f evaluated at x star. And then repeat 2 and 3 1,000 times, or until your steps get really tiny, or some other clever stopping condition. Getting back to our nasty polynomial, suppose we pick a starting point like x star equals negative 0.57. The slope or derivative at this point is negative 0.49. So, assuming we use a step size of 0.13, our first update to x star would look like this. If we repeat this process, you can see how we eventually converge on the function's minimum. Now, suppose the function you wanted to minimize was negative cosine of x divided by x squared plus 10. The derivative of this guy is sine of x times x squared plus 10 plus 2x cosine x divided by x squared plus 10 squared. If you happen to start here, where x star equals 4, using a step size equal to 6, you'll end up converging on the nearby local minimum instead of the global minimum. We won't go too deep here, but this is a big issue for neural networks, and there's a lot of research devoted to avoiding these local minima. Lastly, suppose we have a multivariable function, like f of x1, x2 equals sine of 5x1 times cosine of 5x2 divided by 5 plus 0.25. In this case, we need to calculate the gradient of f, the vector of partial derivatives of f with respect to x1 and f with respect to x2. Then we proceed just like the single variable case, except here we make what's called a gradient step, where we simultaneously move in the best x1 and x2 direction. And as usual, we repeat this process a bunch of times until we converge on a minimum. Let's get back to our neural network model. The thing we're trying to optimize is accuracy rate. To put this in the context of gradient descent, the thing we want to minimize is negative accuracy rate. Unfortunately, accuracy rate isn't a differentiable metric, which means we can't use it with gradient descent. So why isn't accuracy rate differentiable? Well, if you think about a vector of predictions and a vector of true labels, so vectors of zeros and ones, you can't answer the question, how will a small change in one of the inputs change the output? Because the inputs aren't even defined on a continuous range. The concept of a small change in one of the inputs isn't even a valid concept. Secondly, each of the hidden layer nodes and the output node suffer from a discontinuity. As we increase one of the input weights, the output abruptly changes from 0 to 1, or from 1 to 0. In other words, our model isn't a smooth function, thus it's not differentiable. And if our goal is to use gradient descent, we'll need our model to be a smooth, differentiable function. So we need to make some adjustments to our model. First, we'll deal with the discontinuities, where we convert the input to 0 or 1. Graphically, the transformation looks like this. Z here is the sum of the inputs into a single node, and F is the output. The formal name for this guy is the Heaviside step function, and clearly it's not differentiable. With this picture in mind, if you had to draw a differentiable function that basically mimics the Heaviside step function, the obvious choice would be something like this. The class of functions that take the shape of an S like this are known as sigmoids. Two common sigmoid functions used with neural networks are the logistic function and the hyperbolic tangent. We'll proceed with the logistic function, since that's sort of the classical activation function. By the way, these nodes are commonly called activation nodes, and the functions on top of them are commonly called activation functions. Next, we'll address our scoring metric. We can't use accuracy rate, not only because it isn't differentiable, but now that we're applying the logistic function to the output node, our model's going to output a continuous range of values between 0 and 1, which aren't valid inputs for calculating accuracy rate. So we need a scoring metric that meets the following criteria. It needs to operate on input vectors y hat and y, where y hat I is an element in the range 0 to 1, and yi is an element in the set 0, 1. The closer y hat I is to yi, the better the score should be, and it should be differentiable. With this criteria in mind, what scoring metric pops into your head? That's right, log loss. For the uninitiated, given a prediction y hat I in the range 0 to 1, and a true label yi also in the range 0 to 1, the log loss of this individual prediction equals negative yi times log of y hat I minus 1 minus yi times log of 1 minus y hat I. Then the total log loss equals the average log loss across all predictions. I'll use a lowercase l to signify the log loss for a single sample, and a capital L to signify the average log loss for all predictions. Let's think about this a bit. First of all, this is a loss function. So as we improve our predictions, the log loss score should decrease. Secondly, y hat I and yi should both be in the range 0 to 1 because they're meant to be interpreted as probabilities. For us, yi is even simpler because it's restricted to the set 0 or 1. Now, suppose yi equals 0. Looking at the definition of log loss and plugging in yi equals 0, we're left with negative log of 1 minus y hat I. Graphically, that looks like this. As y hat I gets closer to the true label, 0, log loss approaches its minimum value, 0. Now suppose yi equals 1. Again, looking at the definition of log loss and plugging in yi equals 1, we're left with negative log of y hat I. Graphically, that looks like this. As y hat I gets closer to the true label 1, log loss approaches its minimum value 0. Also note that log loss is differentiable for y and y hat in the range 0 to 1. So, as long as our predictions never reach or exceed 0 or 1, which must be true because every prediction comes directly out of the logistic function, then we know our log loss objective function is differentiable. So, log loss conveniently checks the three requirements we had for picking a scoring function. Before we start calculating derivatives, let's update our neural network picture. Now let's revisit our goal. Our goal was to determine how a small increase in W111 would affect our accuracy rate. With our modifications in place, now we want to determine how a small increase in W111 would affect our log loss. That is, we want to know the derivative of the total log loss, capital L, with respect to W111. More generally, if we can determine the gradient of L with respect to all the weights in W1 and all the weights in W2, then we can make a gradient step, updating every weight simultaneously. The first thing to recognize is that since capital L is just the average of the individual log losses, and the individual log losses are independent of each other, the gradient of capital L with respect to W1 is just the average of the gradient of L1 with respect to W1, L2 with respect to W1, and so on. And the gradient of cap L with respect to W2 is just the average of the gradient of L1 with respect to W2, L2 with respect to W2, and so on. So we can shift our focus from capital L to lowercase l. That is, how does the log loss of an individual sample change with respect to small changes in the weights? It may seem a little bit daunting at first, but let's start at the end of our model and work our way backwards. The last thing our model spits out is a prediction. So let's understand how a small change in a prediction affects log loss. That is, we want to find partial Li, partial y hat I. Recall the definition of log loss on an individual sample I is this. So, with some high school calculus, we can determine partial Li partial y hat I to be y hat minus y divided by y hat times 1 minus y hat. Let's put that derivative in our pocket, so to speak. It'll be useful later. Next, let's see if we can determine Z2's effect on the ith log loss. That is, we want to calculate partial Li partial Z2 I1. Well, Li can be written as log loss of y hat I, yi, where y hat I equals logistic of Z2 I1. Notice we have a composition of functions, so we can reach into our calculus tool belt and whip out the chain rule, which tells us if you have two differentiable functions f and g, and f is composed with g, like this, then the derivative of f with respect to x is the product of the derivative of f composed with g times the derivative of g. In Leibniz notation, if z depends on y and y depends on x, then dz over dx equals dz over dy times dy over dx. With the chain rule at our disposal, we find that partial Li partial Z2 I1 equals partial Li partial y hat I times partial y hat I partial Z2 I1. Well, we just calculated partial Li partial y hat I, so the only thing left for us to do is to calculate partial y hat I partial Z2 I1. Recall, y hat I equals 1 divided by 1 plus e to the negative Z2 I1. Again, with some high school math, we can figure out that the derivative resolves to this. Going a bit further, it turns out that this equals y hat I times 1 minus y hat I. This definition is super useful. Why? The thing in the back of our heads is computational complexity. If these derivatives are hard to compute, gradient descent could take a really, really long time. Now, y hat is kind of hard to compute, but we have to compute y hat during the forward pass. So as long as we cache those values, meaning we don't delete them, we can reuse them during gradient descent. Next, let's calculate the gradient of Li with respect to W2. So the gradient is a one-column matrix that looks like this. Once again, we can use the chain rule because we can describe Li as a function of Z2i, where Z2i itself is a function of W2. For example, partial Li partial W2 1 equals partial Li partial Z2i times partial Z2i partial W2 1. Generalizing that a bit, we get the gradient of Li with respect to W2 equals partial Li partial Z2i times the gradient of Z2i with respect to W2. And since Z2 is just the sum product of W2 and X2, the gradient of Z2i with respect to W2 is literally just X2i. putting it all together, we get the gradient of Li with respect to W2 equals partial Li partial Z2i times X2i transpose. Although I'm going to do something cheeky here and reverse the order of these terms because that makes things a little more elegant down the road. By the way, with nearly the same exact logic, we find that the gradient of Li with respect to X2i equals partial Li partial Z2i times W2 transpose. That'll come in handy, so we'll put that in our pocket for later. The next thing we want to figure out is the gradient of Li with respect to Z1i. In matrix form, that looks like this. Let's focus on this first guy. Well, Li equals some function of x2i1, where x2i1 is a function of z1i1. So partial Li partial z1i1 equals partial Li partial x2i1 times partial x2i1 partial z1i1. That equals partial Li partial x2i1 times x2i1 times 1 minus x2i1. Keeping in mind we already know partial Li partial x2i1. Generalizing this, we get the gradient of Li with respect to z1i equals the gradient of Li with respect to x2i, tensor product, this row of partial derivatives. The tensor product here means we do element-wise multiplication instead of normal matrix multiplication. We can replace these partial derivatives with x2i times 1 minus x2i based on the discovery we made earlier about the derivative of the logistic function. And so, reorganizing things a bit, we get the gradient of Li with respect to z1i equals the gradient of Li with respect to x2i, tensor product, x2i, tensor product, 1 minus x2i. Last but not least, we want to know the gradient of Li with respect to W1, which ultimately is going to be a big matrix like this. Going through the same sort of steps as before, we find that it's equal to x1i transpose times the gradient of Li with respect to z1i. Recapping, here are the important derivatives we calculated. And you can kind of see with these arrows the order in which you'd calculate each of these terms. One thing I'll note is that there's a really nice simplification when you do this multiplication. So in practice, you'd probably skip the calculation of partial Li partial y hat I and go straight to calculating partial Li partial z2i1. Also keep in mind that we want to calculate all of these terms for every single training sample. So by the end, we'll have these two arrays, gradient of L with respect to W1 and gradient of L with respect to W2, each of which is a three-dimensional array like these. And then we can average these terms across the sample dimension, reducing them to two-dimensional arrays like these, which represent the gradient of capital L with respect to W1 and the gradient of capital L with respect to W2. And then finally, we can make our gradient step where we update W1 and W2 like this. In order to implement gradient descent, we'll start by building some helper functions, the first of which is the standard logistic function. The logistic function is defined as 1 over 1 plus e to the negative x. Unfortunately, when x is a big negative number, like minus 1,000, Python throws an overflow error because e to the negative x is really big. The fix for this is pretty easy. There's an identity for the logistic function that says 1 over 1 plus e to the negative x equals e to the x divided by e to the x plus 1. So when x is positive, we use the function 1 over 1 plus e to the negative x, and when x is negative, we use the function e to the x divided by e to the x plus 1. Now we can input values like -1000 without getting an overflow error. Unfortunately, we still have an issue. If we do logistic of np.array 1, 2, 4, 8, 16, 32, 64, you can see that once x reaches 32, the logistic function just starts outputting 1. That means for inputs to the logistic function outside the range -32 to 32, there's no discernible difference in the output. This is going to end up affecting our gradient descent algorithm such that some gradients are going to end up being 0 instead of a really small number, and then our model won't know which direction to step to make an improvement. The solution to this is to normalize the input data. There are different ways to do this, but for grayscale values, an easy normalization scheme is just to divide every value by 255 so that inputs fall into the range 0 to 1. Technically, this isn't guaranteed to solve our problem, but it makes it harder for us to stumble upon a 0 gradient. Next, we'll implement a log loss function that inputs two one-dimensional NumPy arrays, y hat and y, and outputs a third one-dimensional NumPy array with the sample or case log loss values. With these helper functions in place, see if you can code up a neural network that learns to identify checkerboards in the simple images dataset. A little word of advice. You'll probably want to implement what's called a gradient checker. The concept goes like this. Suppose you're searching for the minimum of z equals x1 squared plus x1 times x2 with gradient descent. You correctly calculate that the gradient of z with respect to x equals the vector 2x1 plus x2, x1. But you've made an error coding this up. So suppose your starting point, x star, is x1 equals 1, x2 equals 2, which implies z equals 3. And your program incorrectly says that the gradient at this point is 1, 0. The way you can catch this mistake is with a gradient checker. The way this works is you make a small change in one of the elements of x star. For example, you might create a new point like 1.12. Then you calculate z at this new point, which equals 3.41. Now you can estimate partial z partial x1 as the change in z divided by the change in x1, which equals 4.1. Since this value is pretty far off from our analytically determined gradient of 1, we know we made some sort of mistake. Now, gradient checking is slow and expensive, so it's something you only want to do once when you're developing your model, just to make sure you built it correctly. So with that said, pause the video and see if you can implement your first neural network with gradient descent. Here's the code I came up with. Let's break it down. The init method is exactly the same as it was in the last section. The fit method is where most of the changes are. Starting with the function parameters, we gained a step size parameter, which lets us control our gradient descent step size, and iters, which lets us control how many gradient descent steps to make. In this initialization block, note that we divide x by 255 in order to normalize the grayscale values to be between 0 and 1. Then we enter the gradient descent loop, where we do a forward pass, report the log loss, then we do a backward pass where we calculate grad w1 and grad w2, and then we use those gradients to update w1 and w2. The tricky part here is translating the theory we developed into NumPy array operations. The best advice I can give you is just to step through the code with some toy data, and to also spend some time studying NumPy array math so that it doesn't feel like a black box. You can always check out my course, Python NumPy for Your Grandma, to brush up on your NumPy. Lastly, the predict method is nearly the same as it was before, except I incorporated the logistic function, and I added the ability to return the predicted class labels or the predicted class probabilities. Let's see how it performs on the simple images data. As usual, we'll start by loading the simple images data into train and test data frames. Then we'll initialize and fit a neural network with 4 hidden nodes to identify checkerboards with step size 0.3, 10,000 iterations, and random seed 0. And lastly, we'll use the fitted network to make predictions on the test data. In this case, we get a test accuracy rate of about 0.74. Let's try that again, except this time let's set the random seed equal to 1. This time, we get a test accuracy rate of about 0.98. This highlights how, if you're unlucky in your randomly initialized weight matrices, gradient descent can get stuck in a local minimum. But when you get the initialization right, you can see how powerful neural networks can be. Next, let's focus on generalizing our model. Some nice improvements would be support for multi-class predictions, support for multiple hidden layers, and support for stochastic gradient descent. I'll explain what that is and why it'd be nice to have later, but in the next section, we're going to focus on support for multi-class predictions. After implementing a binary neural network classifier in the last section, our new goal is to implement a multi-class neural network classifier. The obvious way to support multi-class classification is just to tackle in a 1 versus rest or 1 versus 1 system, just like we did with the Perceptron. The biggest drawback to this is that it means we'd have to train at least as many models as we have classes, and sometimes we might have hundreds or even thousands of classes. And training hundreds or thousands of neural networks would take a very, very long time. So we'll take a different approach. Suppose that instead of having a single output node in our neural network, we had multiple output nodes, one for each class of our target variable, where the value produced by output node k is the probability of class k. Clearly, this would be a usable multi-class model. The questions we have to answer are, how do we ensure the output probabilities sum to 1? And how do we adjust our loss function and our learning algorithm to support this? Let's think about that second question. For a given input sample, how do we calculate how good or bad a prediction is, keeping in mind we still need to have a differentiable scoring function? Lucky for us, log loss is actually a special case of a more general loss function called cross entropy, which does exactly what we need. For a single observation, cross entropy equals the negative sum over k of pk times log of qk, where pk is the true probability of class k, and qk is the predicted probability of class k. Notice how if k spans 2 classes, this is exactly log loss. For us, exactly one of these pk's is 1, and the rest are 0. So we can simplify the whole expression to negative log of y hat k star, where k star is the index of the correct class. And just like log loss, we can calculate the average cross entropy over all samples. What about the gradient of cross entropy? Well, we want to know how cross entropy changes with respect to small changes in each of the predicted class probabilities. Keep in mind, for a single sample, y looks something like this, and y hat looks something like this. In this case, the gradient of cross entropy with respect to y hat is going to equal this row matrix of partial derivatives, which resolves to this. Notice every term is 0, except for the term corresponding to the positive class, which is negative 1 over y hat. So our updated network diagram looks something like this. The next question is, how do we make sure our predicted probabilities for a single observation sum to 1? just as cross entropy is a multidimensional extension of log loss, it turns out that the softmax function is a multidimensional extension of the logistic function. It works like this. Given a vector of unbounded real values z like this, softmax of z produces a new vector with the same length, where the kth element of the new vector is defined as e to the zk divided by the sum over k of e to the zk. To put it another way, softmax is like a two-step algorithm. The first thing you do is raise e to the power of each element in the original vector. Then, you divide each of those guys by their collective sum. Intuitively, you can think of softmax as a function that squashes values into probabilities, where higher values translate to higher probabilities. For instance, if z was this vector, e to the z would be this vector, and softmax of z would be this vector. Looking back at our neural network, instead of having a logistic activation function at each of the output nodes, we'll have a single softmax function. Note that with softmax, each y hat depends on every z in the last z layer. Next question. What's the gradient of the softmax function? Or rather, since it's a function that maps a vector to a vector, what's the Jacobian of the softmax function? The Jacobian is just the matrix of partial derivatives that looks like this. Well, Sj is defined as e to the zj divided by the sum over e to the z. So if we think about partial Sj partial zk, we can break it into two cases, where k equals j and where k is not equal to j. And with some help from the chain rule and a little algebra, we get partial Sj partial zk equals Sj times 1 minus Sj when j equals k, and negative Sj times Sk otherwise. Now our job is to calculate the gradient of cross entropy with respect to W1 and W2. We'll approach this just like before, starting at the end of our network and working our way backwards with the chain rule. The first step is to calculate the gradient of cross entropy I with respect to y hat I, which we already did. So we'll just recall that CEI equals this. So the gradient of CEI with respect to y hat I is this. And keep in mind that the only non-zero term in this row matrix is the one that corresponds to the correct class. Next, we want the gradient of cross entropy I with respect to Z2I, which is going to be a row matrix like this. We can use the multivariable chain rule to expand these terms into the following, because each z feeds into each y hat, and each y hat feeds into the final cross entropy. But most of these terms are going to be 0, because only one yk is not 0. So if we denote the true class index for the ith sample as k star, we can rewrite this matrix like this. Then we can pull out partial CEI partial y hat I k star, which we know is equal to -1 divided by y hat I k star. So then we have to deal with these terms, which basically ask the question, how does our prediction for the correct class change with respect to small changes in the Z2 terms? Well, the y hat layer comes from applying the softmax function to the Z2 layer. So let's recall the softmax derivatives we found earlier. So with this, we can define partial CEI partial Z2ik equal to -1 divided by y hat I k star times this piecewise function, which ultimately simplifies to this. And then this tells us that partial CEI partial Z2ik equals y hat ik, except we subtract 1 from the term corresponding to the correct label. Well, a sneaky way to rewrite this guy is just y hat I minus yi. Next, let's determine the gradient of cross entropy I with respect to W2. If we think about this first term, partial CEI partial W211, we can use the chain rule to rewrite that guy as partial CEI partial Z2I1 times partial Z2I1 partial W211. Well, we just calculated partial CEI partial Z2I1, so we only need to determine partial Z2I1 partial W211. And that's pretty simple. It's just X2I1. So if we generalize this to the whole matrix, we get this matrix product, which we recognize as X2I transpose times the gradient of CEI with respect to Z2. Next, let's figure out the gradient of cross-entropy I with respect to X2I. Well, this follows nearly the same logic as the last gradient we just calculated. So pretty quickly we can figure out that this equals the gradient of CEI with respect to Z2 times W2 transpose. And then from this point onward, we're really just repeating the same steps we did in the last section, so we can literally reuse our old work. So to recap, here are all the gradients we'll need to calculate. And then our batch update process looks like this, very similar to what we had before. Now let's think about the code. We're going to need some new helper functions, the first of which is softmax. Recall that if you have a vector of values z, and you apply softmax of z, you get back a new vector where the jth value of the output equals e to the zj divided by the sum of e to the z. So we can code up a pretty simple row-wise softmax function like this. Next, we make a one-hot function that inputs a 1D array of labels and returns a tuple of two things, a 2D array of one-hot encoded values and a 1D array of unique classes, where the kth value in the class array corresponds to the kth column in the one-hot array. Next, we make a cross-entropy function that inputs arrays y hat and y. Y hat should be a 2D array of predicted probabilities, and y can either be a 1D array of true indices or a 2D array of one-hot encoded true indices. This function returns row-wise cross-entropy values, so if the input arrays have length n, the output array is also going to have length n. Lastly, we'll reuse the logistic function we created in the last section. Now pause the video and see if you can implement a neural network class that supports multi-class classification with softmax activation on the output layer and cross-entropy loss. Here's the code I came up with. Frankly, there's nothing too earth-shattering in my code. It's pretty much the same as it was in the last section, except I incorporated the softmax function and cross-entropy loss. Also note that the way I determine which class label the model predicts for a given sample is by determining the class index with the highest predicted probability using NumPy's argmax function. Let's see how our multi-class neural network performs on the simple images data. Here, we use virtually the same setup as the last section, except in this case, we use the raw image labels for the target Y instead of binary indicators for whether each image is a checkerboard. After 10,000 gradient descent steps, we evaluate our model on the test data and see that it's about 98% accurate. Not bad. Now that we have a neural network with multi-class support, let's add support for multiple hidden layers. Thinking about our network diagram for a second, how would things change if we added one more hidden layer? Well, we'd have three weight matrices, W1, W2, and W3, that we'd want to optimize, which means we'd need to solve for the gradient of cross-entropy with respect to W1, W2, and W3. Now, if you focus on this portion of the network, you can see it's virtually identical to the network we just solved for. So we actually already know all these gradients. We just have to update their indices. Now we just have to solve for the gradient of cross entropy with respect to W1. Well, if we isolate this portion of the network, it also looks exactly like the initial part of the network we just solved for. So we actually know these gradients as well. The trick here is to write the gradients in terms of the next layer. Notice we never fully expand any of these gradient definitions. The W1 gradient is written in terms of the Z1 gradient. The Z1 gradient is written in terms of the X2 gradient. The X2 gradient is written in terms of the Z2 gradient, and so on. Essentially, what I'm getting at is the neural network has a natural recursive structure. So we can define the gradients recursively, and that'll allow us to implement a neural network with any number of hidden layers. The key to implementing this in code is to cache all of these X's and Z's as you calculate them in the forward pass. So pause the video and see if you can implement a neural network class with support for multiple hidden layers. By the way, when you have a neural network with multiple hidden layers, that's typically what people refer to as deep learning. To get you started, I modified the innet class to use a W's attribute, which is an ordered list of all the weight matrices. And in the fit method, the hidden nodes parameter should now be a list of integers, indicating how many nodes to use in each hidden layer. Here's the code I came up with. The first mildly tricky part is initializing W's, the list of weight matrices. I do it by initializing W's as an empty list with one more element than the length of hidden nodes. Then I populate the first weight matrix based on the shape of the input layer and the number of hidden nodes in the first hidden layer. Next, I populate the weight matrices that go between hidden layers. And lastly, I populate the weight matrix that goes from the last hidden layer to the output layer. I also initialize empty lists to store the Z matrices, X matrices, and grad W matrices. Inside my gradient descent loop, you can see I've implemented the forward pass using a loop with an indexer j that iterates over each layer of the network. Perhaps the hardest part to wrap your head around is the backward pass, i.e. backpropagation, which I've also implemented with a j indexer that iterates over the layers of the network but backwards. If you're having trouble with this part, as usual, I suggest stepping through the code with some toy data. It's essentially the same thing we've been doing, except here we do it repeatedly for each layer in the network. And then the predict method is more or less a subset of everything we covered in the fit method. Let's see how a deep neural network performs on the simple images dataset. Here I'll train a neural network with 3 hidden layers, 5 nodes in the first hidden layer, 3 nodes in the second hidden layer, and 4 nodes in the third hidden layer. In theory, using multiple hidden layers like this should allow the network to learn simple concepts in the first hidden layer, things like edges or lines or blobs, and then in the second layer, it builds off of those simple concepts to identify more complex concepts like corners or triangles or squares, and then the third hidden layer builds off of those concepts to identify even more complex things like circles or connected triangles or squares with stripes. Now, what's really interesting about this is it turns out that any deep neural network you can actually build an equivalent neural network with just one hidden layer, although it may require more nodes. In fact, it turns out that you can use a single hidden layer neural network to approximate any continuous function. This is known as the universal approximation theorem. So if that's true, why do we even bother building deep networks? And in fact, that's the mindset people had when neural networks were relatively new. The reason we like deep networks is because their hierarchical structure allows gradient descent to more quickly fit the network to training data without overfitting. And This goes back to the idea of learning concepts on top of concepts on top of concepts. And so in practice, deep networks tend to perform better on challenging problems than shallow networks. With that said, our simple images dataset is simple, so I don't expect our deep network to add much value over our shallow network from the last section. Sure enough, when we evaluate this guy on the test data, we find it's about 94% accurate. So not as good as our last model, but still pretty good. I should also mention that one big modeling piece we're missing is the tuning process, where you optimize the hyperparameters of your model. So maybe we'd get a higher accuracy if we used 2 layers instead of 3 layers, or if we had 10 nodes in the middle layer instead of 3, or if we trained the model for 20,000 gradient descent steps instead of 10,000. In practice, you'd kind of just try different things and see what other people have been successful using. The important thing for us at this stage is that the model works properly, so we can apply it to other more complex datasets like MNIST. In fact, let's give that a go. Unfortunately, our deep neural network is going to take a very, very long time to train on the MNIST dataset, so we need a way to speed it up. And we'll do that in the next section via stochastic gradient descent. In the last section, we built a deep neural network, but when we trained it on the MNIST dataset, it was slow as hell. That's because the MNIST dataset has a lot more samples and features than our simple images dataset, and so that's a lot of matrix multiplications and other processing for our computer to handle. Now, truth be told, we could make a lot of optimizations within our code, the biggest of which is we're not utilizing any sort of parallel computing. We could even go as far as to use GPUs, which are really good at parallel computing. But even with expensive GPUs, we'll have performance issues on large image datasets. So how can we modify our network so that it can train on datasets with millions of high-resolution images? The common answer here is to use stochastic gradient descent. Stochastic gradient descent is a variation of normal gradient descent, or what some people call batch gradient descent, whereby you update your model's parameters based on the gradient of a loss function with respect to a single training sample at a time. In pseudocode, it goes like this. Suppose we want to minimize some total loss capital L, which is the mean of a vector of case losses, lowercase l, where Li equals some loss function of yi and y hat I. Written another way, Li equals some loss function of yi and f of xi theta. In our case, some loss function is cross entropy, yi is the ith training label, f is our neural network, xi is the ith training feature vector, and theta represents all the weights in our neural network. So then stochastic gradient descent goes like this. First, shuffle the training data. Then for I in 1, 2, 3, on up to the number of training samples, calculate the gradient of Li with respect to theta, then update theta as theta minus alpha times the gradient of Li with respect to theta, and then if your stopping criteria is met, stop, otherwise repeat 1 and 2. Notice how this differs from normal or batch gradient descent, where we compute the gradient of the total loss with respect to theta, which requires us to consider every training sample before we make our gradient step. The downside to stochastic gradient descent is it can take a while to sweep through every training sample. So there's a happy medium between stochastic gradient descent and batch gradient descent called mini-batch gradient descent, which goes like this. First, partition the training samples into random mini batches for b equals 1, 2, on up to n batches, where each mini batch has batch size samples. Then for b in 1, 2, on up to n batches, calculate the gradient of LB with respect to theta, and then update theta as theta minus alpha times the gradient of LB with respect to theta, And then if your stopping criteria is met, stop, otherwise repeat 1 and 2. Here, LB is the average loss of the training samples in batch B. For example, if the bth batch includes training samples 4, 5, and 6, then LB equals the average of L4, L5, and L6. Now, besides the obvious memory and processing benefits of stochastic gradient descent, there's an even more important theoretical benefit. It turns out that the loss surface of many real-world datasets are riddled with local minima. Batch gradient descent happens to be really good at finding nearby local minima and getting stuck there, whereas stochastic gradient descent kind of bounces around and is less prone to getting stuck in these local minima. At this point, see if you can tweak our current neural network class to support mini-batch gradient descent, and then see if you can apply it to the MNIST dataset. To help you get started, I added one little parameter to the fit method called batch size. The default value, none, tells the fit method not to use mini-batch gradient descent. Otherwise, if batch size is an integer like 5, it means use mini-batch gradient descent with approximately 5 training samples in each mini-batch. Here's the code I came up with. It's pretty simple. The first thing to note is I define a variable called inBatches, which represents how many batches of training samples I should partition the training data into. If batch size is none, I set inBatches equal to 1. Otherwise, the number of training samples divided by the desired batch size, rounded up with NumPy's ceil function. Next comes my gradient descent loop that runs iters times. By the way, iters here is usually referred to as epochs, where each epoch represents a full sweep over the entire training data. At the beginning of each iteration, or epoch, I build a randomly shuffled array of training indices and then partition them into a list of inBatches subarrays. From here, I just loop over every batch, picking out the corresponding training data, and execute the gradient descent procedure I set up in the last section. So that's really all it takes to set up mini-batch gradient descent. Let's try it out on the MNIST dataset. In this case, I'm going to train a model with 3 hidden layers with 50, 20, and 8 nodes respectively, step size equal to 0.1, batch size equal to 100, and iters equal to 200. Candidly, training this model is still pretty slow. In fact, it requires a lot more time to reach 100 iterations than batch gradient descent. However, it takes less time to reach a decent accuracy rate. Also, it's a lot more memory efficient, so it's the kind of thing we could scale up to work on bigger datasets. After about 45 minutes, this thing is finally finished training. When we evaluate it on the test dataset, we find it's about 96% accurate, which is pretty good considering I did very little hyperparameter optimization. So that actually covers all the code we're going to write in this course. In the next and final section, I'm going to briefly mention things we could do to improve and generalize our network. And I'll also talk about more advanced neural network concepts that are beyond the scope of this course. Congratulations on making it to the end of the course. In this last section, I want to briefly mention some neural network topics that I didn't have time to cover in the course, or things that are beyond the scope of this course that you can look forward to learning next. There's really only a handful of things that I skipped or didn't cover, such as different activation functions like tanh, ReLU, leaky ReLU, different neural network libraries like TensorFlow and PyTorch, strategies for neural network regression, flavors of neural networks like convolutional neural networks, recurrent neural networks, LSTMs, GANs, GRUs, autoencoders. Then you have applications like object detection, image captioning, text-to-speech, sentiment analysis, text summarization, one-shot learning, reinforcement learning. Oh, and then there's things like batch normalization, savior initialization, root mean square propagation, and adaptive momentum estimation. Okay, maybe there's a lot of stuff I didn't cover, so I'll just pick out a few things to mention and call it a day. First of all, in this course, we used the logistic activation function and we stuck with it. It turns out, when you have a deep neural network filled with logistic activation functions, it can suffer from something called the vanishing gradient problem, where the gradients in the first few layers become so small that they're essentially static, meaning they have an inability to change and improve. The way most people deal with this problem is, instead of using a logistic activation function, they use what's called a rectified linear unit, or ReLU, which looks like this. Now, you might be thinking, hey, that's not differentiable at 0. And you're right, but all we have to do is arbitrarily define the derivative at 0 to be 0 or 1, and then we're good. Another thing you might be thinking is, if we end up in this flat area where the derivative is 0, we'll get stuck there. And again, you'd be right, but in practice, this turns out not to be a big deal because it's unlikely that all of our weights are going to get trapped in these 0 gradient situations. However, because of this, some people prefer to use what's called a leaky ReLU, which has a very minor slope in the negative region. Next, how can we use a neural network to solve a regression problem, like predicting the sale price of a house? In this case, the neural network will typically have a single output node without an activation function. By not using an activation function, the output can grow unboundedly small or large. Also, the objective function you'd use would be something like root mean square error or root mean square logarithmic error. Lastly, how do you know how long to train a neural network? In other words, how many gradient descent steps, or epochs, should you make? So far, when we've trained our neural networks, one of the things we monitored was the cross-entropy loss of the training data. In practice, what we really want to do is, first, randomly remove a small portion of the training records and call this a validation dataset. Then, as we train our model on the training dataset, we monitor its performance on the validation dataset. At no point during the training procedure should we let our model use the validation dataset to calculate gradients and improve the weights. And that's the point. The validation dataset is meant to be an unbiased evaluator of our model as it learns. What typically happens if you monitor the loss on the training and validation data is, as your model learns, the loss on the training data tends to get better and better and better. But for the validation data, the loss tends to get better until a point at which it plateaus or sometimes even starts getting worse. This is an indication that your model is overfitting to the training data. And so the optimal number of gradient descent steps you want your model to make is usually the point at which your validation loss stops decreasing. I've actually added validation monitoring to the neural network we implemented in the last section, and you can see validation loss stops improving after about 125 iterations. Now, it happens that retraining the model for 125 iterations on the full training data gets you about 95% accuracy on the test data, which is slightly worse than the 96% accuracy we got when we trained it using 200 iterations. But when we used 200 iterations, we were essentially guessing a number, and we happened to get lucky. In practice, if you do this, you'll typically underfit or overfit to the training data, and your performance on the test data won't be so good. By the way, this technique is not unique to neural networks. It's a common approach used for any model that relies on gradient descent, including things like XGBoost and LightGBM, which are popular implementations of gradient boosting. So with that, I hope you enjoyed this course, and I hope you got a lot out of it. Creating this course actually took me 7 months of writing, coding, recording, animating, and editing, so it was a pretty big undertaking. Any feedback you can give me, good or bad, would be appreciated. And if you enjoyed the course, consider liking, subscribing, and sharing my content. It means a lot. So thanks, and stay tuned for future content.